Okay, so let's go through the Dijkstra's algorithm, which we went through in class. So let me just quickly go the principle of relaxation of the algorithm. Okay, so as I said, you're going to find the shortest path from the source vertex to every other vertex in a graph, in a weighted graph. By shortest path, we mean the minimum weight path. Okay, so the sum of all the edge weights will be the minimum. And we're going to do that in iterations, and in each iteration we are going to find the shortest path, as I show here. Each time I make a vertex yellow, it means I found the shortest path, right? So in each iteration we are going to find the shortest path to one particular vertex. So we are going to say we have optimized that vertex. And once we optimize the vertex, we are going to do what is called relaxation of its neighbors, which means we are trying to see, using that vertex for which we just found the shortest path, that means which we just optimized, we are going to see whether we can find the shortest path or at least reduce the weight of the path to its neighbors by going through that vertex. Okay, so let's say, so from the source S, we have found the shortest path to a vertex U. Okay, so that's the minimum weight that you can have. So now by going through U, you are going to see whether you can reduce the estimate of the weight of the shortest path to V from S. Okay, so for example, if say 40 has been the weight of the shortest path from S to U, and the weight of this edge is say 10, and if say 90 is the weight of the shortest path from S to V, the estimate that you know of the shortest path from S to V, then what we are trying to see is, by going through U, can you reduce the weight of the of the path from S to V even further, right? So if you go through U, the weight of the path is going to be 40 plus this 10, which is 50. Is 50 less than 90? It is, right? So we no longer need to use this path from S to V that is of weight 90. We can go through U to reach V through a path of weight 40 plus 10, 50, which is less than 90, right? So that is this relaxation step. So we are going to check if, what is that in our case, if this 90 is greater than 40 plus 10. So if 90 is greater than 40 plus 10, we're going to set the weight of the path from S to V is 40 plus 10, and the predecessor of V is U. Okay, otherwise we'll retain the current path that we know from S to V. This is relaxation step. Okay, so let's go through this example and then we'll proceed further. So we have, say, the source S, and we want to find the shortest path, the minimum weight path to every other vertex. Okay, so you have W, X, U, V, and Y. So initially, to start with, the source knows how to reach itself through a path of weight 0, but it doesn't know how to reach the other vertices. So the estimate of the shortest path weight to the other vertices is infinity. All right. So now we are going to start by picking up S, right? Because S is 0 is the minimum of all. 0 is the minimum of infinity, infinity, infinity among all these things. So which means we have found the shortest path from S to S itself, and we are going to see whether by going through S we can reduce the weight of the path to its neighbors. So we are going to do what? 0 plus 3, we are going to check whether it is less than infinity. The answer is yes, 3 is less than infinity. So we are going to reduce it from infinity to 3 and highlight this edge to indicate that S is now the predecessor for W. Similarly, 0 plus 5 is less than infinity. So we are going to make it 5 and make this as the predecessor edge. Similarly, 0 plus 4 is 4 less than infinity. So we are going to update this as a predecessor edge. So now the estimate of the shortest path weight to all these to these vertices are 3, 4, 5, infinity, infinity. So among these, the lowest is 3, which means we pick W as the vertex that we have optimized, which means we cannot find something that is lower than 3 as the weight of the shortest path from S to W. That's the best we could do. So now using that, we are going to see if we can relax its neighbors. The neighbors of W are X, V, and Y. So for X, it's going to be 3 plus 5, 8. 8 is less than infinity, so we can update this to 8 and highlight this edge. 3 plus 3 is 6 less than infinity, we can highlight this edge, and 3 plus 1 is 4 less than 5, which means whatever we know so far from S to V, which is 5, we no longer need to use that. We can go from W to V and update this as 4 and make now W as a predecessor for V. Okay, so now we have 4, 4, 8 and 6, so the minimum among them is 4, so we have a tie. You can break the tie in any order you want, so I just picked up V. Okay, so once I pick up V, now let's see if we can go through its neighbors. Actually, I should have picked up U, right, because this is alphabetical order. So let me make a change here. So, but picking up U would not make any difference though, right? Because if you pick up U, both its okay, so this neighbor is optimized, but if you go through U to reach V, it's going to be what? 4 plus 2, 6. Is 6 less than 4? No. So we just leave it as it is. Alright. So that's not going to make any difference. Now let's make check V now. So for both these three neighbors of V, S, W and U are optimized. The only neighbor you can check is going to be Y. So 4 plus 3 is what? 7. Is 7 less than 6? No. So we just leave it as it is. Okay. If this were say a 1, then I would be what? 4 plus 1, 5 is less than 6. So what we should have done, we should make it 5, remove the highlight on this edge, alright, and do what? And highlight this edge. Which edge? This edge from V to Y, make that as the predecessor, right? Because now we can go through V to reduce the weight of the path even further to Y. We don't do that because what we had was what? 3, right? So 4 plus 3 is 7 less than 6? No. So we just retain with whatever we know. Alright? Okay, so now between 6 and 8, which is minimum 6. So we pick Y as the next vertex that we have optimized. So now the only neighbor you can think about optimize or reducing is X. So we see 6 plus 1 is 7. Is 7 less than 8? The answer is yes. So we can make it 7 and remove the highlight on this edge and make this as the predecessor. Alright? So sorry about that. So you can break the tie with alphabetical order. Okay? Alright, so now we make this as the predecessor. So the shortest path tree is going to be all the bold edges. Alright. Okay, so now let's do the proof of correctness. So before that we need to prove these two theorems that will make use of to prove the proof of correctness too. So the first theorem is a subpath of a shortest path is also the shortest path. So how do we prove that? How do we prove the subpath of a shortest path is also the shortest path? So let's say we have a path from S to D, which is given by S, A, B, C, D, right? So if S, A, B, C, D, given that S, A, B, C, D is the shortest path, given S, A, B, C, D is the shortest path, we want to prove that A to B to C is also the shortest path. Okay, so assume the contradiction that there exists an alternate path from A to C of weight less than the weight of A, B, C. If that is the case, we can go from S to D, S to A through whatever the hypothetical path that we know exists of weight less than A, B, C, right? This path A to C is what I mean by this. So whatever the path from A to C that is of weight less than A, B, C, we can make use of that path to go from A to C. So from S to A through that hypothetical path from A to C, and then we can go to D, which means the weight of this path is going to be less than the weight of what we started with, S, A, B, C, D, which means this is no longer the shortest path. This will be our shortest path, right? That's a contradiction to our assumption that S, A, B, C, D is the shortest path, which means if S, A, B, C, D has to be the shortest path, then A, B, C is also a shortest path. Okay, so that's why the subpath of a shortest path is also a shortest path. It's also the shortest path. Okay, so the next thing is when we say a vertex V is picked up for relaxation optimization during an iteration of the Dijkstra's algorithm, which means we say that we have found the shortest path from S to V, right? So what we now, that's the next proof, but when we say a vertex V is optimized, right, which means all the intermediate vertices that is on the path from S to V are also optimized. Okay, so we have to prove that when we say a vertex V is optimized, which means you have found the shortest path from S to V, all the intermediate vertices on the path from S to V are also optimized. Okay, so how do we prove that? Again, prove by contradiction. Let there be a vertex X for which we have not yet optimized. Okay, so and X is on the path from S to V. So Dijkstra's algorithm picks up the vertices in the increasing order of the shortest path weight. If you see this example, it started with 0, then with 3, then with 4, then with 4, then 6, then of course it reached 7, right? So every time it picks a vertex, right, the weights are increasing, 0 to 3, 3 to 4, 4 to 4 again, then 6, then 7. So when it picked V, right, it means every other vertex that is out there that has not been yet optimized is having an estimate of the weight of the shortest path either equal to the weight of the path to V or more than the weight of the path to V. So which means if X has not been yet optimized, the weight of the shortest path to X should have been greater than or equal to the weight of the shortest path to V. It cannot be what? It cannot be less than this, right? So, but from theorem 1 that we just proved, the subpath of a shortest path is also a shortest path, and it could be a direct edge from X to V, or it could be a sequence of vertices from X to V. All those edges that form the path from X to V have to be of positive edge weights. That's another assumption of Dijkstra's algorithm, right? All edges, especially those that are not attached to source, have to be positive edge weights. So if the weight of the path from S to X is itself greater than the weight of the path from S to V, and then these edges are going to be of positive edge weights, then that's not going to be possible, right? Because then this contradicts the previous theorem that the subpath of a shortest path is also a shortest path. No, right? So every intermediate vertex, all right, on the shortest path from S to V, if we pick up V, that intermediate vertex should have also been already picked up. Okay, which means the estimate of the weight of the shortest path to X should have been less than V. Okay, so only if it has been picked up earlier, its weight of that means it's already optimized, its weight, shortest path weight would be less than the shortest path weight to V. If it has not been picked up, then the weight of the shortest path to X would be definitely only greater than or equal to the weight of the shortest path to V, right? So which means that will even further increase the weight of the path from S to V. That is not possible, right? So the vertex X should have been already optimized. That's what it means. Okay, so now let's prove this thing, the proof of correctness of Dijkstra's algorithm. So we have to establish here, when we pick up a vertex V, right, to optimize, to relax during an iteration, to be the vertex with the lowest weight among all the vertices with the estimated path weight, right? We say that we have found the shortest path from S to V. So how do we prove that when we pick a vertex among the vertices that have the lowest estimate for the shortest path weight, that we have found the shortest path from S to V. Okay, so which is basically the crux of the algorithm, right? So each time we pick up a vertex, right, when I pick up W, which is the minimum weight among 3, 4, 5, 20, and 20, I say I found the shortest path to W. Similarly, when I pick up U of weight 4, which is because it's a minimum among 4, 4, 6, and 8, I say that I found the shortest path to U. Similarly, Y and so on, right? So when I pick up a vertex with the minimum weight among the vertices that are yet to be optimized, I say I have found the shortest path to that vertex. How is that possible? How can you prove that? That's what we're going to prove now. All right. So let's say the path that we find that through Dijkstra's algorithm from S to V to be the shortest path is, say, path P. So now let's say that there is again a better path P prime such that the weight of P prime is less than the weight of P. So now we have to argue whether such a hypothetical path P prime can really exist. Okay, so we have only two scenarios that we need to look at. One scenario is what? Every intermediate vertex in the path P prime is already optimized, or there exists at least one intermediate vertex in the path P prime that is not yet optimized. Okay, so we'll see both the scenarios. The first scenario is if every intermediate vertex in the path to P prime is already optimized, then what would have happened? Okay, every intermediate vertex would have a weight of the path, right? So let's say so on this path P prime, okay, so you have S through some vertex X to V, right? So if every intermediate vertex on the path from S to V is already optimized, we can say that the weight of S to X is less than the weight of S to V, because we picked up X, right, ahead of V. So which means by using X, we could, that's what Dijkstra's algorithm does too, right, before it picks up V. Why? Because this is on the path P prime, right? This is on the path P prime, and this is even further less than the weight of the path from S to V on what? On the path P, right? So when Dijkstra's algorithm picked V as the next best vertex that you have optimized for the shortest path, Dijkstra's algorithm would have already picked up X, right? Because the weight of X to X is less than the weight of X to V. So which means Dijkstra's algorithm would have explored reducing the weight of the path to V by going through X, right? So for every intermediate vertex on the path from S to V, they would have been optimized by Dijkstra's algorithm before it picked up V. So it would have considered reducing the weight of the path to V by going through all those intermediate vertices, which would make what? The weight of the path from S to V in path P prime will be only equal to the weight of the path P, because every intermediate vertex that you have used here would have been used to explore the weight reduction. Okay, so the weight of the path from S to V on P prime can be only equal to the weight of the path S to V in P, right? But our assumption is the weight of P prime is less than the weight of P, so this scenario cannot exist. So now let's look at the alternate scenario, that is there exists a intermediate vertex X which is not yet optimized. Okay, now if there exists an intermediate vertex that is not yet optimized on the path P prime, we have just shown that the previous stage when you find the shortest path, right, from S to V, right, the subpath of the shortest path should also be a shortest path, right? So the weight of the path from S to X has to be the weight less than the weight of the shortest path from S to V. So if X is not yet optimized by Dijkstra's algorithm, right, then the weight of, this is of course on the path P prime, but according to what we have, X is not yet optimized in path P prime, whereas we assume that we have found the shortest path from S to V, which is less than the weight of path P that Dijkstra's algorithm finds for us. So if X is not yet optimized by Dijkstra's algorithm, the weight of the path from S to X, right? So on P prime, this has to be true, right? Weight of X to X has to be less than weight of X to V, because X is an indeterminate vertex on the path from S to V. But from Dijkstra's algorithm point of view, the weight of the path from S to X should be greater than or equal to the weight of path from S to V. Alright? Which means the weight of the path from S to X to V in P prime has to be greater than or equal to the weight of the path from S to V in P, because from S to X itself it's going to be greater than the weight of the path from S to V in P, right? So X to V is going to only have positive edge weight. So from S to V in P prime, the weight of the path is going to be only greater than or equal to the weight of the path S to V in P, which is a contradiction. S to V in P prime we have established has to be greater than or equal to the weight of the path S to V in P. Contradiction to this, right? So this scenario cannot also exist. So that path P prime is only imaginary, cannot exist such that weight of path P prime is less than weight of P. Okay, so what are the path that you find by Dijkstra's algorithm is the optimal path. Okay, so that's the proof. Let me see.